Hi, welcome to lesson 23. So now that we've kind of talked a little bit about the mechanics of confidence intervals, we're going to actually outline what are the steps, what does a template look like, and actually run through a couple of examples. So when you want to use a confidence interval from mu, and it's really important that this is a confidence interval from mu when you know the population standard deviation. So when you want to estimate the average value from a single population. There are conditions, so there are those three conditions. So you need to have a random/representative sample from the population. Two, it's really important that your sample size is big enough that you can trust that the central limit theorem is going to kick in for the sampling distribution of x bar. And then, the third condition here is knowing sigma of x. If you don't know the standard deviation from the population, that's going to be a problem. And then remember, sometimes it's going to be weird language like varies on average. If you see that language in a problem, that's talking about the standard deviation. It's just a weird way to say it. So the confidence interval, once you decide, okay, I meet those conditions, this is going to be the setup. So x bar, so this is your point estimate from your sample, times z star, so that's my critical value, and we'll have a table in just a second, times standard deviation of x bar. It's equivalent to if you plugged in sigma from the population over root n. So z star is a critical value from the standard normal. So if you want a 90% confidence interval, you use a z star of 1.645. If you want a 95, you're going to use 1.96. If you want a 99, 2.576. A lot of people don't necessarily memorize these. It's not something that we require. It's more of like write it down is probably a good idea. Have it somewhere. If we were on campus and having exams in the same way, we would basically just have you write it down on your note sheet. And so this is just the image that goes with it. The z-scores associated with the correct percentiles to give you the middle 90%, 95%, and 99%. Are just these values that are here in our table. So choosing a confidence level. So most of the time, at least in this class, we will use a 90% confidence, 95, or 99. And we're going to talk about there are trade-offs either way. So the level of confidence that you pick, it's a trade-off between precision and accuracy. So we're going to stick to 90, 95, and 99. That's pretty much the most common. Every once in a while you'll find a weirdo who's super excited about their 98% confidence interval. But let me assure you, that's kind of uncommon. Most people don't have intervals that aren't 90, 95, 99. So the higher the confidence, the wider the interval gets. So think if you're 90% confident, hey, I have this range. But if you're 99, you're 90 plus some. So just to kind of illustrate here, here's an example. We have a 90% confidence interval. The 95 is the 90 plus some. So it's a little wider than the 90. And then the 99 is the 95 plus some. So the higher that confidence level goes up, the wider it gets. You're more certain that the interval's in it because you're using a wider net, right? So then there's the point estimate, right? So this is just x bar for us. It's very precise, right? It's not a range of values. It's just one value. It's exact. But it's not accurate as much, right? It's wrong a lot of the time versus if you actually use a range of values. And then you can have an 100% confidence interval, but it literally goes from negative infinity to positive infinity. It goes on forever in both directions. it's like the equivalent of saying like, hey, what is the average test score out of 100? And I said, I have 100% confidence that the average is between 0 and 100. It's one of those, it's not useful because it's so wide that it just can't be useful. So definitely we usually go between 90, 95, and 99. So just a note, like the 90, so out of these three, the 90% is narrowest, so it's more precise, but it's less accurate, so it's less likely to have it because it's not as wide. The 99, it's more accurate because it's wider, but it's less precise because it's wider. And then the 95 is somewhere in between. So it's relatively accurate and precise. I would say 95% is often like a default. If we don't list a confidence level, you can generally assume a 95% confidence interval. But also, if we don't list one, feel free to ask. We aren't trying to, be hiding that. So when I'm talking about precision and accuracy, and I have a visual on the next slide there, precise talks about, so the more precise it is, the smaller the interval, right? So, it would probably be more useful for folks if they wanted to find out, what's the average test score? If I said, hey, it's between, 60 and 100, that's not very precise. Versus if I said, it's between 78 and 82. That's a lot more precise. It's a lot narrower of an interval. And then accurate, this talks about we want to have, a high success rate for capturing the true mean mu. So if I were to take lots of random samples and calculate whatever level of confidence, I want a really high, rate that these confidence intervals actually have the real population mean in it. So just outlining again, so if I want a 90% confidence interval, my z-star is 1.645. It's more precise because it's narrower, but it's less accurate because it's narrower. 99, it's 2.576 as my z-star. It's more accurate because it's wider, but it's less precise because it's wider. And things to note, the 90%, 1.645, 95, 1.96, then 2.5. The z-stars are getting bigger, and when the z-stars get bigger, the interval gets wider. So what I'm talking about, precision and accuracy, just like a little target example. So you can have a combination, so you can have very precise, but as you can see, it missed the center of the target, right? So it's precise, but not accurate. You can have something where if you look, on average, the points are all kind of right there, but it's not very precise, right? They're not very tight packed in there. So you have low precision and higher accuracy. This is our sad place. We don't like this place. We don't like having low precision and low accuracy. So that's like saying having a really wide interval and the rate that these intervals even have the real mean in it, it's really low. That makes us really sad. This is our happy place. We like to have high precision and be accurate if we can. So how can you affect these at all? With precision, usually if you just increase your sample sizes, it'll be more precise. But accuracy is trickier because accuracy, in order to be accurate, you have to reduce any sources of bias that are present. So you need to make sure that you're sampling correctly. You need to make sure if it's an experiment that you're randomizing treatments and whatnot. So accuracy has everything to do with if accuracy goes up, bias goes down and vice versa. So here are our steps. We're going to go through these steps every time when we want to solve estimation problems. Estimation just make you think confidence interval. So the first step, so we read the question prompt pretty much. And then we're going to state our question of interest. I usually, I pose it as a question. For estimation type problems, a lot of times it'll be like, what is? That kind of thing. Like, hey, what is the average height for all OSU students? It's something that has an open-ended answer, right? You wouldn't answer yes or no. You would answer with a number or a range of numbers. And then 2, you want to identify the parameter of interest that we, like, what is it we actually want to estimate? And then take inventory. So this is where you figure out, okay, well, here's the problem, here's the information they give us. In this class, 1, 2, or more populations, we're going to stick to 1 population in this class. And then the type of variable, so if it's a categorical variable that you're collecting, so like yes or no, or political party, or whether you prefer hot or cold, you're going to be trying to estimate the proportion. This is some week 10 stuff. And then if what you're measuring is quantitative, you're going to be dealing mostly with means. Other classes, you might touch on medians as well, but we don't talk about those particular tests. So then you want to check the conditions, because you don't necessarily want to, use that setup where it's X bar plus or minus Z star and whatnot if you don't meet those conditions. It wouldn't be appropriate to use it. Basically, you would get an unreliable interval if you don't meet the conditions. And then you want to state the confidence level, because you need to know what Z-star you need, right? Then you calculate the interval, and then this one is super, super important. After you calculate the interval, you need to go back and actually make sure you answer the question. And for me, that's something I constantly have to ask myself, because I will just barrel down a side quest there. Ask yourself, okay, I got an answer. Did I answer the question, though? So the example we're going to work through first is a zinc concentration in a river example. So there's an ecologist, and they're really interested in the zinc concentration in a specific river. So they go ahead, they randomly select 36 locations on this river, and they collect samples, and they calculate the average zinc concentration of those 36 locations is 2.6 grams per milliliter. And then it is known, so this is what I'm saying, it is known that zinc concentrations vary on average 0.3 grams per milliliter. Vary on average, this means standard deviation. It's a weird way of saying it, but that's a standard deviation. So find the 95% confidence interval for the mean zinc concentration in that river. So stating the question of interest. So I'm going to put it out there, and then I'm going to talk about the pieces. So what is the average or mean? Totally cool if you put mean there instead of average. Zinc concentration of all locations of this river. So because I'm looking at doing a confidence interval, and they're interested in finding out what is, and then I need the parameter. So mean or average. Zinc concentration, this is my variable of interest. This is what, when we take those 36 locations, is recorded for each of those 36 locations. And then this last part of all locations in this river, that's my population. So whenever you write it up, it should have all of those components. It doesn't always have to be in that order, but we are going to be looking like, hey, did they ask a yes or no question, or did they ask open, like what is? And then we'll look for mean or average, and we'll look for zinc concentration, and then we'll look for the population, so like where they sampled from. So just to know, like, so X is the zinc concentration of a location. So my parameter of interest. This has 2 parts. So mu, this is my notation. So if we said, hey, write it in symbols or notation, we mean this, just the mu part. And then in words or context, the mean concentration of all locations of this river. So depending on how you worded your question of interest, you pretty much just drop the what is. And that's it. The mean is important. Zinc concentration of our population. So that will be what we're looking for. And then inventory. I thought it would fill. So here, I'm going to fill, okay, my sample size, I took 36. What do I want to put next? I have varies on average. So it is known. It is known usually implies we're talking about a population as well. So it is known zinc concentrations vary this much. So I don't know how it's known, but it's known. A lot of times it's from previous studies. So grams per milliliter. And you can totally write out the words. I get a little lazy sometimes. So then, what else do I have? I have X bar. So I had 2.6 grams per milliliter. So things to note too, well, I could calculate sigma of X bar. Definitely make sure you check the conditions, otherwise you don't want to use, well, it still would work. So 0.3 divided by the square root. Oh, let me write the notation. So sigma over root n, and that's just going to be 0.3 divided by the square root of 36. Oh, isn't that nice? You get like 0.05 grams per milliliter. So note, I mean, except for sample size, I mean, the units are going to stay grams per milliliter. And honestly, this is really just, I really like to hold on to these units because, well, one, it's important, and it's really easy to lose the context of the problem and have a hard time, like if you're looking at something you did before, having any clue what it's about. Okay, so my conditions. So do we have a representative sample / random sample? So looking here, here it is with 36 randomly selected locations. Yes. Is the sample large enough for central limit theorem to kick in? So we don't know how the population is shaped. It doesn't say there, but our sample size is 36. So that's bigger than 30. So yes, it's going to be big enough that central limit theorem is going to kick in. And do we know the population standard deviation? Yes, that's that sigma is 0.3 grams per milliliter. So yeah, we know that as well. So state our confidence level and respective critical value. So if we want a 95% confidence interval, that means we're going to use a z star equal to, and this is just from that table. It's not necessarily, you don't have to do a calculation every time with this. It's just from the table. 1.96. So putting all this in here, 2.6 grams per milliliter, 0.3 grams per milliliter, 36, 1.96. Just rewriting this, so 0.3, 0.05. So there are all my parts that I'm going to need. But just in case, so here, if I want to calculate the interval, so x bar plus or minus, so I'll have z star times. So I'm just going to plug, since we already did this math, that 0.05 straight in. But absolutely you can put 0.3 over the square root of 36 in there as well. So that's going to be equal to, So 2.6 is the sample mean from the sample, plus or minus, so 1.96 times 0.05. And so it's really important to do the multiplication first. I know order of operations, it's old school, but like make sure you do multiplication before you do addition or subtraction, because it will steer your calculation in a very wrong direction very quickly. So I'm doing some math. Get something like 2.6 plus or minus 0.098. So if I put it into interval notation, so that's where we have the parentheses. So parentheses and then the lower one. So 2.6 minus 0.098. It's 2.502 grams per milliliter. Trust me, I'm not doing this in my head. I had a calculator. So 2.6 plus, so 2.698 grams per milliliter. So in this, this is interval notation. If we say, hey, write out the confidence interval in interval notation, this is what we mean. Parentheses, lower number with units, comma, higher number with units, parentheses. So that's what we'll want. So now we have to write up, like we have to actually answer the question, right? Because we said, hey, what is the average zinc concentration for all locations in this river? We have to write a sentence that makes sense to answer this. So here's a template. I really can't stress enough, like this is going to be something you use a lot. So I really strongly remind you to use this here. So the blank % confidence interval, so it doesn't have to be this exact wording, but it has to hit all, like every blank thing that we have you fill in is something we will look for. So if the sentence makes more sense to word differently, okay, but we are going to look for all these components. So the blank % confidence interval for the true, that's us saying like, oh, it comes from the population. So parameter, usually mean. And then the variable of interest, so what we're measuring. So here it'll be zinc concentration of, all locations on this river is on average estimated to be between whatever your lower bound is with units and upper bound with units. And then this part's important too. So with a point estimate of whatever your sample mean is with units. So now we're going to apply this to the river example. So here, you see 2.502 grams per milliliter, 2.698 grams per milliliter. Okay, so for me, it's really easy to plug in the 95 first. The 95% confidence interval for the true, and I'm looking at a mean. So the true mean, it's okay if you write average, that would be fine as well. And then variable of interest, so zinc concentration. So where did these samples come from? All locations on this river. Is on average estimated to be between, so the lower one first, 2.502. I didn't have enough space, so I'm going to write grams per milliliter abbreviated. And 2.698 grams per milliliter. With a point estimate of, so this is X bar from the sample, 2.6 grams per milliliter. So put it all together. Our 95% confidence interval for the true mean zinc concentration of all locations on this river is estimated to be between 2.502 grams per milliliter and 2.698 grams per milliliter, with a point estimate of 2.6 grams per milliliter. So later on, this would be our two-part write-up for a confidence interval. this is one part and this is the other part. As long as you include all of those things, it really doesn't matter the order. Although it should be a coherent sentence. You really do want to be readable. Okay, so here we have a second example. And just to show you, I know nothing about zoology, or at least I didn't. There's a small group of 15 Allen's hummingbirds. I thought this was a dude named Allen who had a bunch of hummingbirds. No, it's a type of hummingbird. So there's 15 of them, and they're being studied over in Arizona. And they take the average weight of these hummingbirds. I'm not really sure. I never see them sit still. And that's 3.15 grams. So they're very light. Based on previous studies, we can assume that weights of all Allen's hummingbirds have a normal distribution, that's handy, with a standard deviation of 0.33 grams. So usually whenever they refer like, oh, it is known, or previous studies show, we can usually relate that to the population. But if we weren't sure, that all kind of helps out. So the researcher of this study, they want to estimate the true mean weight of all Allen's hummingbirds. So calculate the 99% confidence interval for the true mean weight of all Allen's hummingbirds. So we're going to go step by step. So we're going to start off, what is our question of interest? Okay, so we're going to go step by step. We're going to start off asking, what is our question of interest? So here, they want us to calculate a confidence interval, and they told us that outright. So that means that the question we ask should be like a what is type of question, open-ended. So my question of interest, what is the average or mean weight of all Allen's hummingbirds? So there's that what is, kind of indicates it's an open-ended question. Average or mean. And then my variable of interest, we're weighing them, so weight. And then my population, all Allen's hummingbirds. Whether or not these 15 hummingbirds represent all Allen's hummingbirds, that's a whole other issue, probably worth a disclaimer at the end. So step 2, what's my parameter? Well, if I'm taking weights, this should be quantitative. So I'm going to have mu. So mu is going to be the mean weight of all Allen's hummingbirds. So it's really cool because if you word your question of interest carefully, your parameter of interest is hanging out right there. Same thing. So then I'm going to take inventory. What information do I have? So real quick, I took 15 hummingbirds. Those 15 hummingbirds, I saw an average weight of 3.15 grams. The abbreviation is just G. And then I know that the population is a standard normal distribution with, a normal distribution with a standard deviation of 0.33 grams. And then I can go one extra step. I can calculate sigma of x bar. That's just sigma of x, which I have over square root of n. So 0.33 over square root of 15. So let me check. That is not doing my head kind of math. Rounding 0.085. You could probably go out more spots. That's where I'm going to go, at least for right here. So now we need to check the conditions, right? We don't want to go and use these z methods and calculate it using a z-star, just to find out that we shouldn't use a z-star. So first off, I'm going to skip the first question actually. I'll come back to it. I'm going to start with, is n large enough for the central limit theorem to kick in? So n, our sample size was 15. think I have to stop. So with the sample size of 15, we're going to need to know something about the population, right? Because it's not over 30. So hopefully, if we look, based on previous studies, we can assume the weights of all owl and hummingbirds have a normal distribution. So based on that, the sample size of 15 is going to be big enough because the population follows a normal distribution. 3, do we know the population standard deviation? Yes, they told us, hey, we know that it's normal and it has this standard deviation, so 0.33 grams, so yes, we do know it. But now we're turning to question 1. Was this a random sample? So suppose a small group from 15 owl and hummingbirds has been under study. It doesn't sound like this was a random selection, and quite honestly, with wild animals or animals in general, or even humans, it is incredibly difficult to get a true random sample because you have to be aware of all of the hummingbirds in the population in order to randomly sample them. So, probably not. In general, though, know that people will brag if they did randomly sample. It's almost always like people don't randomly sample and not mention it. If it's not mentioned, never assume they randomly sampled. Never assume they did it correctly. Honestly, it's hard to do it this way with like hummingbirds, but probably not. So this is going to be worth like an asterisk at the end, like maybe not all Allen's hummingbirds. Oops. I'm going to run out of space. Assume that says hummingbirds. It's very sad. Okay, step 4, the confidence level, 99%. This means we're going to use a Z-star of the big one, right? So 2.576. So yeah, 1 wasn't met. We're still going to proceed. It's just that when we do our write-up, it's probably worth writing like an asterisk at the end saying, hey, this may not apply to all Allen's hummingbirds. I'm not even sure that it applies to all of them in Arizona because it sounds like they're just a very specific set of hummingbirds. So here, 2.576. So calculate my confidence interval. So x bar plus or minus, so z star times, sigma of x bar. Look, we have all the components right here. That's pretty cool. So that's just going to be 3.15 plus or minus 2.576 times 0.085. I don't think I actually rounded in my calculator. So if you go ahead, you subtract first, you're going to get your lower bound. So something like 2.93 grams. In general, at least 2 places past the decimal is a good place to go. And then up to 3.37 grams. So it is important to, 1, have the units, but 2, also the order matters, right? You don't count from big numbers to small numbers, so we want the lower number to the higher number. It's always worth, not most of the points, but it's always worth something if you reverse the order, because the orders, like I don't count from 10 to 1. Most of the time I count from 1 to 10 kind of idea. So now we need to write this up. Oh, filled it in for me. Okay, so here there's more decimals there. So the 99% confidence interval, definitely the easiest part to fill in. For that was like a mean or an average. Either one would be okay. the mean what? Weight of all. I'm going to write it in terms of the population, but then I'm going to have an asterisk. Allen's hummingbirds is on average estimated to be between 2.931 grams and 3.369 grams with a point estimate. So what did I see in the sample? 3.15 grams. And then asterisk, only applies to sample. You want to be careful though, because the write-up for the confidence interval should never be in terms of the sample. It should always be in terms of the population, always. You want to be very, 15 hummingbirds. So you do want to be careful. A thing to note too, smack in the middle, like exactly in the middle, is the point estimate. So if you ever have a confidence interval and your point estimate is not exactly in the middle, something went wrong with the adding and subtracting part. So just might be handy a little later, like, hey, what is, the point estimate? They give you an interval. Just average the endpoints. Take the average, you get the middle. So a few notes about confidence intervals, because they can be tricky wrapping your head around the idea of them and talking about them. So the units for the bounds of the confidence interval are the same as the units for the sample mean. So like the hummingbirds, the sample mean was in grams. So the confidence interval was also in grams. You also want to be super careful, like what does the confidence interval say versus what it doesn't say. So it doesn't mean that the mean is in this particular interval 95% of the time, because in reality it's either in there or it's not. It's not 95% of the time it's in there. It's just 95% of the intervals we make using this particular method work, have the actual mean in them. So it doesn't say 95% of the sample data are in the confidence interval. That's absolutely not going to be true. It's not, yeah. And it doesn't say that you're 95% certain the sample mean is in the interval. I'm 100% certain the sample mean is in the interval because that's the point estimate, and the point estimate is in the middle. So you definitely don't want to say the latter one. So there are a lot of reasons like why these are complicated. Like these won't work. It's more about confidence in the process. So it's not, hey, this particular sample and this particular confidence interval. It's saying I'm this, 95% of the time or 99% of the time we make an interval taking a random sample. It does have the mean in it. So what you're doing is you're kind of crossing your fingers and hoping you have one of the good ones. So calculating the sample size. So there is the scenario where someone says, hey, I want to make, a 90% confidence interval, but I want to control how wide that interval gets, right? They're like, oh, I want an interval, but I don't want it any wider than, 10% or, whatever it is that they're measuring. So when they have that in mind, they have a margin of error in mind. They don't, I want to be able to estimate it within 5 points. That's a margin of error, that within amount. Okay, so we're going to go ahead, we're going to use the river example to explore this. So we have an ecologist, they're interested in estimating the zinc concentration in this particular river. We're ignoring this sentence about what they collected. We're pretending they haven't collected anything yet. And then it is known that zinc concentrations vary on average 0.3 grams per milliliter. So 0.3 grams per milliliter. That's my standard deviation for the population. That it is known is kind of the giveaway for me. they would like to calculate a 95% confidence interval. So that means we want a z-star of 1.96. And we want to know, hey, what's the smallest sample size we can get away with that we can ensure that our interval has a margin of error no bigger than, I have no idea why it had 0.3 on the slide, 0.04 grams per milliliter. In the notes it should say 0.04. So what this is saying is, hey, I don't want my my interval to be any wider than so 0.04, 0.04. The entire interval, because it's 2 margin of errors long, is not going to be any wider than 0.08. So I mean that might be pretty precise. I'm not entirely familiar with zinc concentrations. So I'm going to start off here because n is the thing I don't know. So z star times sigma of x over the margin of error, and I'm going to square it. That's equal to, just plug in the number, so 1.96 times 0.04, oops, 0.04, it goes down here, 0.3 squared. So in general, whenever we say, hey, show us setup/work, this is a lot of what we're looking for right here. Is we want to see what numbers you plugged in and where. We don't have to see necessarily every single step, but know that the less that's shown, sometimes it means less partial credits available if anything goes wrong. So doing this math, I plugged it into a calculator. We get 200 something, 216.09. So just putting it back together, so n is greater than or equal to 216.09. Haven't quite finished answering the question yet. So things to think about. 216 won't be enough, right? If you need a sample size of at least 216.09, 216 locations won't be enough. You also can't randomly sample 216.09 locations, right? You have to sample a whole number. So always round up. So always round up. If it's a whole number, you can keep it. But a lot of times when you do this math, it's a decimal. So need to sample at least 217 locations on the river in order to ensure that our 95% confidence interval won't be any wider than, have a margin of error any wider than 0.04 grams per milliliter. So that would be like what we mean by calculate the sample size. And as far as any sample size calculations, I mean, that's pretty much, it's going to be in the context of confidence interval questions. So yeah, I think that's going to be it for, a couple of notes. I think I already said this. So bonus slides, they're your turn. So we have stuff on grading times and I think also chips. We have a chips example. We really, really love it. So I hope you enjoy it too. So I look forward to talking with y'all and hopefully adding to the discussion board.